Hi, I'm Dallin, and we're going to be talking about the volume of a cone. Let's get to it. Okay, so the volume of a cone is given by pi r squared h over 3. R being the radius of the base, and h being the height of the cone. If you're curious of how I get that, just be warned, this is very math intensive. Okay. So we have a cone here. Notice that, you see here, not this part, but this part is a cone. Notice how it's made up of a bunch of circles that get increasingly smaller in radius. Now, if this were an actual cone, it would actually go up to a point, but this thing is in the way, so it doesn't actually go up to a point, but you know what I mean. Like, circle, then smaller circle, another smaller circle. We can actually get the volume of the cone by taking the area of each individual circle, and then adding up all of them, which, quite frankly, is difficult to do because there is an infinite number of circles, because circles are 2D and a cone is 3D. We can actually represent the volume of a circle, though. Okay, so we express each of these could, in fact, not be a circle in 2D, but a really, really, really thin disk in 3D. I assume you already know the way how you get the volume of a cylinder or a disk, which would be h being the height of the disk times the base area of the disk, which is given by pi r squared. Okay, so we get r squared and times pi as the base area, but the height, because this is a really, really, really thin disk, you get the height of the entire cone, and there's an infinite number of disks, so we just divide that by infinity. Looks really weird, I know, but yeah. And we use every single possible r between 0 to c. We're going to call the radius of the actual of the base of the cone c. This is c. We're going to use every possible r from 0 to c. And note, since we're using every possible r and 1 r per disk, that actually eliminates the problem of having infinity in the denominator, because the infinity represents the height divided by how many disks we have, and there are as many disks as we have and that's how many disks we have. So when you multiply that by infinity, those cancel out, actually. Normally we wouldn't do that, but that's actually the exact same number, so that exact same infinity, so we can do that there. So that really turns out to be pi times h times the average value of r squared between the interval of 0 to c, which we'd actually be able to explain with a graph. Would be the area under the graph divided by this value c, because that's how many you're going over. The average value would be the area divided by this. Okay, so turn to a graph. And I have two different ones of these set up. To enlarge and for greater accuracy, I made two squares, one instead of just one square. Okay, so we're going to count up all the squares under it to find the area under the curve, then to find the average value of the curve. We're going to divide by how many x coordinate, the x coordinate of this point. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then we're going to estimate this. This isn't exact, but we're going to estimate it. So this and this make 1. So 14, then 15, then let's call this 15 and a half. Okay, so 15 and a half into this, then 16, 17, 18, 19, 20, 21, 22, 23, then 24, then another half, so that will be 25. Then 26, 27, 28, 29, 30, then 31, then 31 and a half, then 32, 33, 34, 34 and a half, so it'll be 35, and let's call this another one, 36, then 36, 36 and 1/3. So that would make the average value in this 36 and 1/3 divided by 1, 2, 3. That would be around 12. And also note that this is 1, not just this. And so we actually need to divide this value by 4, because 4 of these make 1, not one of them. So it'll be 12 over 4 equals 3. This value of c is 3. So we multiply, and so we find c squared, that's equal to 9. And 9 over 3, that equals 3. I would show this to you, but we're running out of time. So the average value would be c squared, but divided by 3, because it's not going, because the average value is 1/3 of c squared, not actually c squared. So be c squared over 3, then times pi h. So that's how we get this. Let's put this to the test. Okay, so I measured the radius of the base radius of the cone to be 2.5 inches, and then the height is also 2.5 inches. So this should theoretically be theoretically be 15.625 pi over 3 cubic inches. Let's see what the volume actually is. 1, 2, 3, 4, 5. By the way, that's approximately 16 cubic inches. 26, 27, 28, 29, 30, 31, 32. About a teaspoon of water actually leaked out the bottom, which is how much actually fits in the spout, which is not part of the cone. A teaspoon is half of a a tablespoon is half of a fluid ounce, which is the same as a cubic inch. And so there were 16 fluid ounces or 16 cubic inches of water in here, which, as the formula predicted, is the correct amount.